Hello, everyone. It is my pleasure to start the one and only session about physical aspects of brittle fracture. We will begin with a two-in-one presentation made by Sherman from Israel. So the presentation will last 25 minutes, and then we will have time for questions. And I will give you a small sign to tell you that you remain 2 minutes. And okay, you are already prepared. Thank you very much.
Okay. Thank you, Mr. Sherman. Thank you all for coming. I'm going to talk. My name is Sherman. I'm from School of Mechanical Engineering at Tel Aviv University, Israel. I'm going to talk today on macro to micro in fracture, macroscopic fracture properties versus microscopic bond-breaking mechanisms along the crack front. My second title is Shorter is Tougher. Usually, it is used to say that smaller is stronger, but I'm talking about toughness. As the crack is getting shorter, then it becomes tougher. The cleavage energy increases. This is the bunch of PhD students that made the work over the years. And we start. So first part is macroscopic fracture properties. And I want to start with very short, 3-point short introduction. The first point is Griffith theory of brittle solids, 1921. I don't know if you know, but here Griffith had a mistake in the first paper. He put knee mistakenly in the equation, but he corrected it in 1924. This is a bit of history. So I'm not going to talk about all the Griffith theory. Griffith is for initiation only, and it is made by using thermodynamic energy balance. This is the specimen. This is load control conditions, very important to notice, because we have here sigma, which is constant. And oops, yeah. And this is the equation. Griffith was the first to define the critical stress needed to initiate the crack. And the main idea and the brilliant issue that he introduced is 2 gamma surface, twice the free surface energy of the material, because a crack generates 2 free surfaces. Here, this is the crack. The first times anybody showed that the strength is a function of the crack length or the flow length. What I'm going to show is that 2 gamma surface is only the lower bound of the possible energy to initiate a crack. It might be even 3 times higher. I hope I will manage to convince you. Something is wrong with the controller. Okay. We can if the crack is under environment instead of 2 gamma surface, which is served for vacuum, it can be also 2 gamma stress corrosion cracking, the environmental and cleavage energy. Okay, so we claim that Griffith barrier of gamma naught, I'm using gamma naught as the cleavage energy, equal to gamma surface, is the lower bound of the cleavage energy. This is actually a mantra. All the world know that gamma naught is 2 gamma surface. We will talk about it. We also attempted to evaluate the upper bound of the cleavage energy, but here you should go to very short crack, and we cannot test a specimen with very, very short crack. We will see it in a minute. There are 2 papers in this subject already, one from 2023 and the other from this year. The second point, oh, there is another issue. Okay. Griffith claimed that sigma criti, the tensile strength that the crack initiated using it, times square root of A is constant, and we will examine it also. I just want to show some short information from Griffith paper. This is Griffith paper. He tested spherical bulbs and circular tubes, and he wrote 2C. This is the crack length here and here, and sigma square root of C. Sigma square root of C, and I plotted it. It doesn't seem constant to me, and I will talk about it also. Well, but that's the way it is. Here, this is a very small portion or very small variability of the crack length, so we'll see that. The second point is Irving energy release rate, G. Once again, it is under load control. G is minus d pi over dA, where P is constant. Pi is the complementary energy or the potential energy. And I want to stress out some points about G naught, the energy release rate. It is a function of geometry, the stresses, distresses, the initial crack knot, the initial crack length A naught, the temporal crack length, and at V equal 0. It is quasi-static. It is not dynamic. For material problems. So this is very important to know. Sigma is constant. It is load controlled. It is load control under constant because the crack has no the loading has no time to change during very fast crack propagation. And another issue is that A naught is very important also. Sigma itself is sigma of A naught. As the crack is getting shorter, the stresses are getting higher. This is very important to understand. And G naught is actually linear with crack length, assuming that the specimen is large enough. And what we claim that actually initiation occurs when G naught equal gamma naught. And I'm asking, is gamma naught always equal to gamma surface or to gamma stress corrosion cracking upon initiation? The third point is what we call theta. Theta is the gradient of G naught. We know it as the measure of stability of the crack. Load control, it is positive, therefore the crack is unstable. Displacement control is negative, and therefore the crack is stable. But we are using it as an important variable in our experiment. So theta is actually minus d squared pi over dA squared, and it is constant, and I will show it in a few minutes. Okay. Shorter pre-crack, higher stresses, higher theta upon initiation. Theta is a new macro scale variable related to A naught. And I'm going directly to a macro scale experiment. This is our experimental system. We have aluminum plate, 100 by 100 by 10 millimeters cube with rectangular hole. The specimen is 42 by 25 millimeters square. This is the specimen cut from silicon wafers. The pre-crack is generated here by thermal shock technique. And then the specimen is glued by 2 epoxy resin layers, cured for 4 days. and then it is ready to be tested. How we test it? After curing the epoxy resin, we put it on top of electrical heating stage, and in several degrees C, the crack will have sufficient forces due to thermal expansion coefficient mismatch. If you hold it with your hand, the crack will propagate. So don't do that. The stress field is nearly constant across the whole area of the specimen. What is very important is this issue. Here we have G naught, the strain energy release rate, joule per meter, not strain energy release rate. This is load control. G naught is a function of A for various A naught, which is the pre-crack length. If we have a long pre-crack, 10 millimeter and above, which is about quarter of the width of the specimen, we will have very small theta. Small theta it means that for delta A, certain delta A, you have very small additional energy for any crack propagation. Gamma naught is here. This is gamma naught. But if the initial crack length is longer, then you have much higher energy to dissipate for the same delta A, and gamma naught increases. If you decrease more the pre-crack length, what you have a huge energy to dissipate during the crack propagation of the same length, and gamma naught increases. So you can see this is schematic, but this is exactly as it is during the experiment. So you can see here between 2.5, between 2 to 5, this is short, 5 to 10 medium, larger than 10 is a long crack. So you immediately see here that shorter is tougher. You can see it here already. Okay, let's go on. This is just to show you the relationship between theta and A naught, the initial crack length. And you can see that it increases very rapidly for very short pre-cracks. We are using theta to demonstrate our experimental result. Something else we are doing now, after many years of working, we are doing chevron notch of both sides, and then we have a beautiful, very symmetric pre-crack length. This is the crack front, and the crack front is curved. This is a very important issue in the whole analysis. Okay. So we evaluated the energy speed relationship by measuring crack speed using Wallner line method or potential drop technique. This is only for very slow cracks, but this is for fast cracks. So we're using both of them here to have V over CR. This is friend equation of motion, if you are not aware of it. G over 2 gamma surface is evaluated, G naught is evaluated by finite element analysis. So what we do, we actually evaluate V by using this information. CR time, no, we know, okay, we evaluate G naught, we know gamma naught, so we can evaluate V. Our experiments were done with silicon specimens. It is 100 silicon specimen. The crack was propagating along 2 low energy cleavage planes. This is This is 11111 minus 2 silicon cleavage system. This is the plane, and this is the crack front direction. And what we can see here is this data. This is normal. This is V, not normalized V, because we don't have unique gamma naught. And this is G naught, not over gamma naught, because we have several gamma naughts. So here, this is the experimental results are the full lines, and the dashed lines represent trend equation of motion for certain gamma naught. You pick up gamma naught until it fully fits, and then you get gamma naught. Here, this is theta. This one is theta because the crack length is long, so theta is low, 0.88. And if you do, for example, crack length of, where is it? Here. This is 7.15, then we reduce to 6.15, we get gamma theta 2 instead of 0.88. And what we see that this crack is initiated at 6 joule per meter square. This one is at a bit over 3.5. 2.2 is the cleavage energy under environment. So what we see here is that the crack increases the energy from 2.2. It initiates by 2.2. You cannot avoid it. But it starts to be dynamic only at 6 joule per meter square. And here, what we know about fracture of brittle materials is that you have two stages. One is initiation, the other is propagation. And what we claim is that we have in between quasi-propagation. So actually, the crack is starting here and propagating for about several microns at very low speed, because actually the driving force is the temperature, it is the heating temperature. We heat it by 1 degree C per minute, so it may take 2 minutes to reach from here to here. So there is an additional mechanism, quasi-propagation, and the same goes for the second. The same goes for the second cleavage system, 110, 1 - 10. I'm not going to talk about it. It's the same results. So what we can conclude from here that gamma naught is gamma naught of theta. Gamma naught is gamma naught of theta. And if we draw gamma naught versus theta, you see that we have a straight line. And this is the cleavage energy under vacuum. It is not cube. The cleavage energy under vacuum, this is the cleavage energy under environment condition. And we reach here 7.5 in terms of gamma naught over 2 gamma stress corrosion cracking. It increases by 3.5 over the free surface energy under environment. The same goes for 1 - 10. And look at the slope. The slope here is 1.52. This is CDS, we call it CDS. The slope here is 2. This is due to atomistic arrangement at the crack front vicinity. Okay. Now we can, instead of writing V over CR, I forgot to say something. This is very important. We can now call gamma naught of theta 2 gamma stress corrosion cracking plus CDS times theta. If we now put it in front equation of motion, gamma naught, instead of gamma naught, we put this equation, we can actually see that the speed, energy speed curve is shifting to the right. And now, instead of doing curve fitting of each curve, we put theta and xi, and we get the whole curves. We don't need to do a curve fitting here. We have exactly the result. This is for 111. This is for 110. Okay. So we also examine a few other things. For example, we relate sigma as a function of A naught. Sigma was obtained by finite element analysis at this point. And what we see, this is the Griffith relationship, gamma naught equal to gamma surface. And here, this is our experimental result with gamma of theta, and we have very nice fitting. In addition to that, if we evaluate sigma square root of A as a function of A naught, we get, we don't see that sigma square root of A is constant. This is very new graph. Okay. Okay. So I've done with the macro scale experimental results, macroscopic fracture properties. Gamma naught is a function of theta, which is itself a function of the crack length. Not only. I want to now suggest a mechanism that enables increasing of the cleavage energy in crack system. Okay, I call it microscale modeling. So why theta is higher for a higher, why gamma naught is higher for higher theta, and how gamma naught increases over true gamma surface. Let's first see the problem. This is half of the specimen. We have pre-crack A naught. The crack is propagating along this area. This is very important, curved crack front. Also, the mechanical crack, due to the mechanical loading, is curved. Its curvature can be changed during crack propagation in order to increase the energy. Okay, so the most important issue is that when you look at the fracture surface, you see that the crack front is curved. It is never straight. There is a few broken specimens, and you can see the fractures, the crack front in metallic materials, in steel and in aluminum. Crack front is never straight. Okay? If crack front is never straight, we can do some assumptions. B and C here, this is 110. B and C is about 15 microns behind A, B and C. 15 microns, that's it. By the way, the crack front will be straight only when Poisson ratio in the direction will be 0. But I don't know many materials with 0 Poisson ratio. This is 111, and this is 112. The curvature here exists also, but it is smaller because Poisson ratio in this direction is smaller in 111 of silicon than in 110 of silicon. So what does it mean? Remember that this is a single crystals made of small cubes attached together. So what happened here? In order to, oops, you don't see it so good here. You see that to show a curve, you must have some steps. You must have some steps. We call it kinks. The height of the, by the way, it is very important to understand it. the kinks are planar in the plane of the crack propagation. It's all the time planar. So the height of the kink is 1 atom. The length is about 20 atoms in our case. What you have here, kink advance in this direction, advance or migration. And here, this is kink formation or nucleation in this direction. I have 5 more minutes.
You still have 5 minutes before the end of the talk.
I still can talk 5 minutes.
If you want questions, you should stop soon.
Yeah. 0. I can talk. Okay. So kink advance is propagating parallel to the crack front. The energy to propagate kink advance is only a bit over 2 gamma surface. But kink formation is much higher, and it should be nucleate using thermal fluctuation in the material. I sketch E formation is higher than E advance. This is I try to sketch it somehow. I hope it is better understood. Okay. The only way to form curve front in crystals is by generating atomistic planar steps or kinks. The thickness of the specimen is 680 microns. It has hundreds of thousands of kinks. We did not invent the kinks since first introduced in the literature in 1975 by Sinclair. Okay. So here, this is the mechanisms. This is a crack front. I'm looking at this point. This is the macro scale. Micro scale, you see crack front kink steps. And atomistic scale, you see bond breaking mechanism in this direction, and bond bending mechanism in this direction. This requires much higher energy since this is straight line. And here, the atom already in big tension. So they can break immediately when they reach 2 gamma surface. Okay, so if you have a crack front with no kink formation, with no kink nucleation at all, then the crack will reach certain propagation only by kink advance and will stop because it has no sufficient energy to propagate. But when it has a higher than 2 gamma surface energy, here, this is G naught, about 2 gamma surface, a bit below. This is G1 greater than G naught. So maybe one nucleation is sufficient to absorb the G naught. Then if G naught is higher, you need to have more and more energy formation or kink formation in order to absorb all the G2 energy. And if the energy is very high, all the front is made of kink nucleation, and the crack became straight at high energy. Okay. This is actually, we actually evaluated G naught by a simple rule of mixtures. From macro scale, gamma naught equal to gamma stress corrosion plus CDS. In micro, E formation times F plus E advance 1 minus F. I'm not saying that this is very accurate, but this is only a way to show that it is possible. And probably much work should be done by it. I don't see if you can see any analytical model. Okay, so here we actually defined F, the number of, or the relative number of formation when this is exceed DS and theta, and gamma formation minus gamma advance. I will shorten the talk. We have here several types of G naught over A, G naught over A. I think something is, no. Okay, here this is for long cracks, this is for medium size crack, and this is for short cracks. And each one behaves differently.
I'm sorry.
We have also tau curve behavior. I'm not going to the end.
Yeah.
And
sorry.
I leave the
It is time
summary.
to conclude.
You asked me about the summary, so I will say a few minutes.
Thank you, Mr. Sherman.